First, let's read the problem together. Two 20.0 gram ice cubes at negative 17.0 degrees Celsius are placed into 350.0 gram of water at 25.0 degrees Celsius. When we read the problem, we realize that there are two parts for this problem. One part is the ice cubes. The other part is the water. As a general principle, you want to make your calculation as simple as possible. Therefore, it is a good idea to separate the calculation of the ice cubes from the calculation of the water. Let's do it now. I write down the ice cubes on one side, and I write down the water on the other side. I also draw a line to separate the two columns. The mass of the ice cubes is 20.0 gram multiplied by 2 because we have two ice cubes. And the initial temperature is negative 17.0 degrees Celsius. The mass of the water is 350.0 gram, and the initial temperature of the water is 25.0 degrees Celsius. Assuming no energy is transferred to or from the surroundings, calculate the final temperature of the water after all the ice melts. The final temperature of the water is what we are looking for. The heat of furan is 6.01 kilojoule per mole. Furan is the physical change from a solid to a liquid. Therefore, we should put down delta H furan on the ice cube side. The molar heat capacity of water is 75.3 joule per mole per Kelvin. And the molar heat capacity of ice is 37.7 joule per mole per Kelvin. As you may have already noticed, I assign a symbol to every number of its unit. This will help us to find the right equation to use, because all the equations contain symbols, not numbers. Next, we are going to do some analysis to see if we can find any hidden information. We also want to know what kind of calculations we need in order to find the solution for this problem. We may need to read the problem again. When we read, all the ice melts, this tells us that the ice cubes will change from a solid state into a liquid state. It also tells us that the water will remain in a liquid state. This is because if the water will turn to a solid state, the ice will not melt. And also, from what we have learned in class, when you mix anything together, they will reach the same final temperature. Therefore, the final temperature of the ice cubes will be also TF. And also, from what we have learned in class, when you turn the ice cubes from a solid into a liquid, they will absorb heat. Let's call this heat Q1. The problem says, assuming no energy is transferred to or from the surroundings. This indicates the heat the ice cubes absorb will be equal to the heat released by the water. Let's call the heat released by the water is Q2. We should have Q1 equal to negative Q2. Let's see what kind of calculations we need in order to find the solution for this problem. In order to calculate the heat, we have 5 equations to use. The first 3 equations can be used to calculate the heat whenever there's only temperature change, but no phase change. Equations 4 and 5 can be used to calculate the heat whenever there's only phase change, but no temperature change. In other words, all the equations can be used to calculate the heat whenever there's either only temperature change or phase change. If we look at the water, we have a temperature change, but we do not have a phase change. So we can finish the calculation in one step. But for the ice cubes, when we change from solid to liquid, we also have a temperature change. In order to calculate the heat for this process, we have to break it down to different steps. And for each step, we either have only temperature change or phase change. A good separation point will be the melting point, because we have a change from solid to liquid. As we know, the melting point for water is 0 degrees Celsius. For the first step, we can have temperature change but no phase change. And for the second step, we can have phase change but no temperature change. And for the third step, we can have temperature change but no phase change. Since we already have Q1 and Q2, let's call these steps A, B, and C. Now let's put down the information into appropriate places. Let's look at the water. We have no phase change, we only have a temperature change. Therefore, we should put down Cm here. This is the molar heat capacity of water. Then, let's look at the ice cubes. For step A, we have ice. Therefore, we need to put down the molar heat capacity of the ice here. For step B, we only have a phase change. So we put down delta H fury. And for step C, this is in liquid state. So we should use the molar heat capacity of the water, not the ice.